topic is n-queen problem using backtracking. Now, what is n-queen problem? N-queen problem is the problem of placing n queens onto n by n chessboard so that no two queens attack each other. Now, this is the case when the queen is going to attack, the queen will attack either horizontally or vertically or in either of the diagonals, like as shown in here in the case of red arrows. That means no, the queens will attack each other if they are sharing the same row, same column, or any of the diagonal. Now queen can move either, just like the queen of the chessboard, it can either move vertically, horizontally, or diagonally with any distance. Now, how to solve this n-queen problem using backtracking? We'll start with uh, the first queen. If the queen is 1, that is 1 by 1 chessboard, that n-queen problem, 1 queen problem is not applicable. Now, if you are placing two queens, first queen, let us suppose you placed here, second queen you can neither place here nor here. If you are placing second queen somewhat here, so this will have a diagonal attack of the queens. If you are placing second queen somewhat here, there will be vertical attack of the queens. So for n is equal to 2, n queen problem is not applicable. Similarly, consider the case of three queens. Two queens have been placed on this chessboard 3 by 3. You have to place at the exactly three queens on this chessboard. Now you can't place the third queen either here because this will lead to horizontal vertical attack from this side or diagonal attack from this side. Similarly, you can't place the new queen here. This will have a diagonal attack from this side or vertical attack from this side. Similarly, you can't place the queen at this position. It will have a diagonal attack from this side. That means for 3 by 3 chessboard, if you are placing 3 queens, it is not a possible solution. Now considering the case of 4 by 4 chessboard, where you are trying to place 4 queens. Now how this 4 queen problem can be solved using your backtracking problem? It is a demonstration of the same. Now in this example we are entering every row queen row by row. First row, then second row, then third row and fourth row and so on. You can either start by putting the queens in column wise also. Both the directions are feasible one. Now here in this example we are positioning the new queen row by row. Now starting with the first row, we will position the first queen at the first position. There is no chance of attack, reason being this is the only queen which is placed so far on the chessboard. Now placing the next queen on the second row, how it will work? In the first, if you are trying to place the second queen on this second row first column, there will be attack, that is a vertical attack from the previous queen. So this is not a feasible position. Now we will try to find the position of the second queen in the forward direction. We'll try to place the second queen somewhat here. Still it is not a feasible position because the previous queen will attack the new queen diagonally like this. This is not the right position. Then we will move forward this queen one step ahead. Now this is the appropriate position to place the second queen on the chessboard in the second row. Reason being there is no diagonal attack on neither side. There is no horizontal attack like this, and then there is neither any vertical attack. Now the third case is you have to place the third queen at the third row. How to place? If you start placing the queen at the first column of the third row, there will be again a vertical attack from the previous queen. This is not a feasible position. If you move forward this new queen horizontally, still this is not a feasible position because the new queen, that is the third queen, will be attacked by the previous second queen like this in the diagonal manner. This is not the appropriate position. If you try to move ahead this and try to place the queen in this direction, in this position, so this is again not a feasible position, like there is a vertical attack. And similarly, we can't place the queen at this position, reason being there is a diagonal attack. That means it is not possible to insert the third queen in the third row in this current scenario. So what is the remedy for this? We will do the backtracking concept here. How to backtrack? That means no insertion is possible. So backtrack means we need to change the position of, that means this position of the second queen in the second row is not the appropriate one. Because of that, we are not able to insert the third queen in the third row anywhere in the third row. So what to do in this case? Backtrack and try to change the position of the second queen. How to change the position of the second queen? We'll moving it forward somewhat. Let us suppose we move it forward like this, and again try to apply now the concept. Now placing the third queen at the third row in this position, still it is not a feasible solution because there is a vertical attack. If you try to place the third queen at this column in the third row, this is the appropriate position because there is neither any diagonal attack nor any horizontal and vertical attack. So next is positioning of the fourth queen in the fourth row. Now if you start positioning at the in the fourth row, first column, this is not the appropriate position because there will be attack, that is a diagonal attack. Now if you try to move it forward and try to place the queen at this position, there will be a vertical attack. If you move it further and try to place the queen in the next column, there will be again diagonal attack. If you try to place the queen and move it forward, there will be again a vertical attack. That means the insertion at the fourth row is not feasible for the fourth queen. That means this is not the appropriate, previous one is not the appropriate position. We'll do the backtracking and we'll backtrack it and try to change the position of the third row queen. Now when you are changing the position of third row queen, we'll try to position the queen in this position. It is not the appropriate position because there is a diagonal attack, and this is also not the appropriate position because there is a vertical attack. That means the position of the second row queen will have to do backtracking. The position of the second row queen is not appropriate one, but there is no further feasible position in the forward direction. Now what we are left with, we have to now discard this position also. That means we have to alter the position of the first row queen. Now first row queen will be moved from this direction to the second forward direction in the second column. Now try to position the second queen in the second row. This is not the feasible position. This is not the feasible position. This is not the feasible position. This is the appropriate position for placing the second queen. Similarly, for the third, placing the queen at the third row, this is the appropriate position because there is no attack from either diagonally or horizontally or vertically. Now positioning the fourth queen at the zeroth column will lead to vertical attack, there will be diagonal attack. This is the appropriate position for the fourth row. Now this is one of the solution where you are able to place all the four queens in 4x4 chessboard in a feasible manner. So this is the one possible solution. There can be many other possible solutions by altering the positions of the respective queen and so on. Topic is state space search tree for 4 queen problem. Now let us consider this chessboard which is 4x4, and we want to place 4 queens on this chessboard, that too row by row. You can try the same using column by column also. Now the initial root node states that no queen has been placed so far on the chessboard. This is the root node. Now there are not total 4 options to place the first queen in the first row. That first option is you can place the first queen in the first row and the first column, or you can place the first queen in the first row and the second column, or you can place the queen in the first row and the third column, or you can place the queen in the first row or the fourth column. Now we'll be exploring this the first case. If you try to explore this first case, after level 1, in the level 2, this level 2 states that you are placing the queens in the second row. Second row means you can either place the queen in this situation. For the second row placement of the queen, you can't place the queen at this column number 1. Reason being, there will be a vertical attack. That first is position is not feasible. Now going to the second position, this position is also not feasible because there will be diagonal attack. Going for the third position, that is the third column in the second row, this position is feasible for the queen. That's why this has been shown here. And similarly for the fourth case, this position is also feasible for the queen. There won't be any attack. That means these are the two possible options for the same. Now considering this case, there are if you are considering this case, you want to place the queen in the second position. At second position, like second row, you can't place the queen at this position. That's why cross is here. You can't place the queen at this position. That's why cross is there. You can't place the queen at this position. That's why the solution is not possible. But you can place the queen in the second row at this position without any attack. So this is the further feasible partial solution. Similarly, you can explore the cases for these and these. Now, considering the level third level, after third level, you can consider for the fourth level. In this level, if you want to place the queen in the third row, if you want to place the queen in the third row, this position is not possible. That's why this position is also not possible. This position is also not possible. This position is also not possible. That means all the 4 positions for placing the queen at the third row for this current pattern, it's not feasible one. Now considering this uh, pattern for the queen, if you want to place the new queen at the third position, third row, the queen here is not possible because of diagonal attack, but at this position queen placement is possible like this. There won't be any attack. And for this position, queen placement can't be done at this column. There will be a diagonal attack. And similarly, there won't be any placement of the queen at this position. That is, fourth is also not a possible solution. Similarly, in this case, when you try to insert a queen in the third row at this position, this is a feasible position. You can place the queen without attack here. For the second position, you can't place the queen here because there will be vertical attack. For the third queen, you can't do any placement of the queen at this position because there will be diagonal attack. Similarly, for this position, there will be a vertical attack here. Now, considering the next level, now if you want to place the queen at the fourth row, here for this current situation, you can't do the placement of queen at this because there will be vertical attack. You can't place the queen here. There will be again a vertical attack from this queen side. That means this solution is also not possible. You can't place the new queen here also. There will be diagonal attack. You can't place the queen here because there will be vertical attack. That means no solution is being possible to place the fourth queen. Now considering this solution, you cannot place the queen at this position because there will be a vertical attack. You can't place the queen here. There will be a vertical as diagonal as well as vertical attack. You can place the queen here because there won't be any attack. This is the output of placing the queen at the fourth row and the third column. And even this fourth position is also not possible. because you can't place the queen at the fourth position. There will be a vertical attack from this side. Now basically how this whole of the state space tree, how the simulation basically works. The system starts with the root node, and it used depth first search for the same. It tried to place the queen at the first position. First this pattern is executed, then second pattern, because these are not possible options, second pattern which is being generated is for using DFS is this one. Then it does, because there is no possible solution, the system does backtracking and move to the third solution like this. Then it tried to print the next feasible solution, that is the fourth solution. Then there is no further possible solutions are there, it does backtracking, then backtracking, and then again backtracking and try to explore the second solution. In second solution, the fifth step, and the feasible solution after this is this one, the sixth step, and the feasible solution after sixth is the seventh step, and the feasible solution after seventh is the eighth step. This is the final possible solution for placing all the four queens on 4x4 chessboard. After this, it does the backtrack and backtrack and backtrack and backtrack, and it tries to explore the next possible set of position for the queen one and explore it further, and it will do DFS traverse search for the same, and will do backtrack and try to explore the rest of the situations of the first queen onward, and it will come back to the root node. This is the whole procedure how DFS works in case of backtracking. Now if you consider state space search for this 4 queen problem, you can write the same using this notation by representing the indexes of the rows and column where the queen will be placed. Now possible indexes for the placement of this root node. Possible indexes for the first node can be either 0 0, or it can be 0 1, or it can be 0 2, or it can be 0 3. Now when you are exploring 0 1, the once this position is being there, now the other positions can be to place the second queen on the second row. It can be 1 0, or 1 1, or 1 2, or 1 3. But out of this, only feasible are 1 2 and 1 3. Similarly, make as we discussed in the previous slide, make this representation as a whole and try to now trace the same using DFS. Now how DFS will work? First it will start with this one. It will try to explore this position for the second queen. It's not feasible. Second queen not feasible. Not feasible. Then it is feasible situation. Then it will try to explore further for the third queen. This is not possible situation. Not possible situation. Not possible. This is a possible situation. But there is no further solution for the same. It will do backtracking position, and it will try to explore 1 comma 3, 1 comma for 1 comma 2. This is a position for 1 comma 2. It will try to explore all the four possible cases which are leading to no solution like what has been shown here. And for 1 comma 3, this is a queen position for 1 comma 3, index 1 comma 3. There are again four possibilities, and out of four possibility, only second possibility is valid. There are four possibilities. Out of four possibilities, second possibility is the valid one, and this fourth possibility will further lead to no solution, that is 3 0 3 1 3 2, or the no solution for the same. Now considering the second case where queen is placed at 0 column and first row, 0th row and first column index like 0 comma 1, there are four possible ways: 1 0 1 1 1 2. These are not the possible solutions, and 1 3, placing the row at the second column and the that is the first index row and the third index column. This is a valid position. Now this will further have four possibilities. First possibility will be 2 comma 0, that means placing the queen at the position 2 comma 0. Second, third, fourth, these three possibilities are not valid one. You can cross these also, these three one. Now once you will be exploring this, you have explored this case, that is you have placed the queen at the second position. For this case, there will be four again choices will be there. First is not valid, second is not valid, third is valid, and fourth is also not valid. Fourth should be 3 comma 3, which is not a valid position. Now, in the similar way, it will be going for depth first search for the same. It will start with the root node, then it will continue with 0 comma 0 first node, then all these are invalid. This will be further processed to 1 comma 2 because these are not promising solution, these are non-promising nodes. Then from 2 comma 3 there is further no valid solution to backtracking. From this backtracking come to this place 0 0 and then try to explore 1 comma 3 and so on. This pole represents the state space search tree for 4 pin problem. For this case, you can either explore till this only once you have got the answer to 3, 2. You can stop further exploration if you want exactly one solution for solving that queen. If you want to explore further all the cases further, you can explore these cases also, and you can do backtracking and explore these rest of the positions of queen. That is at the third position in the first row and the fourth position of the first row. This scenario will explore all the possible cases in state space search tree. That's all for the session. The topic is implementation of n-queen problem. The first thing is we have to check whether the queen which is to be placed at a particular position has got a safe state or a not. That means, for example, in this case, if you are placing a queen at this position, it should not share same row or same column or same diagonal positions with respect to other queens. That means two queens should have different rows, two queens should have different columns, and they should bear different diagonals also, diagonal positions also. That is how to find diagonal position, that if the queen is somewhat here and queen is here and queen is here, the difference of these values x1 y1 and will be equal to x2 y2 will be equal to x3 y3 and so on. So the difference of the absolute value of this x2 minus x1 should not be equal to y2 minus y1 if you want that queens are being placed not on the same diagonal. Now this is the C program code for placement of n queens on n by n chessboard. Basically here we are storing the result in a linear array where this array represents that as we are storing every new queen row by row, that means we merely have to take into account the final positions as the column values of the respective queens, because row is being automatically being incremented one by one as we keep on adding queens into the chessboard. The result section result array represents the column positions of the and queens which are being stored at their respective places, which are being placed at the respective positions in the chessboard. Now how this algorithm works, the one main function in this is place queen. In place queen we will be passing the array where we will be storing the final result and the zero index. Zero index means that zeroth queen has to be placed at proper position and the chessboard size is n, that is n by n chessboard size. Now this function what it will take, this x represents the x queen which is to be index placed queen which is to be placed at the proper position. This size represents the size of the chessboard. Now there will be one for loop which will be executed. We will check whether for before placing that x queen at the position row x comma, it will start searching for all the possible column values. Now this i's represent here the column 0 till n minus 1 column it will be invoked. If it is getting a safe state, that the queen will be positioned at the particular index of the chessboard, and accordingly the result section will be storing that column index If all the queens are placed, you can print the solution. Otherwise, this place queen function will be again invoked to place the first index queen onto the chessboard. This whole procedure is being repeated within a for loop, and this procedure is being invoked until all the queens have been placed. Now coming to isSafe function here, isSafe function just returns true or false, that is 0 or 1 value. In case if you want to place a new index queen, that is x2 index queen, into the y2 column, whether it is you can place that x2 index queen into the y2 column or not, will it return true if there is a safe state. If that state is unsafe, it returns 0 value. Just dry run of the code is that place queen initially will be starting with the 0 index queen, and the size of the chessboard is 4 by 4. That first queen will be placed at the 0 index. IsSafe function for 0 index column will be returning 0, will be returning yes, as this queen can be safely placed at the 0th column. That means result I, that is result for the 0 index queen, that is the first queen, will give the value as 0. 0 means the 0th column will be used for placing this queen. 0 means the first queen in the first row is being placed at 0 index column. Now afterward, once this first element has been placed, there will be recursive call to place the second queen, that is first index queen, uh, at the proper position. First, the system will check to place the first index queen at 0th column, like this. It will give the unsafe state, the result will be false, and it will try to place this first index queen at first index I is equal to 1. This will return again false, and again it will try to print the first index queen at position at column I is equal to 2. Here it will be returning yes, that is value as 1 here. That means the first index queen, that is the first index queen, can be easily placed at column index 2. Now afterward, the program will move further to place the queen at third row, or I can say second index, into the proper position. Now after placing the previous queens, now third queen has to be placed. Now isSafe function will return for I is equal to 0 false value, because there is an attack by the other queen, and for the I is equal to 1 column, it will again result in attack function, there is a diagonal attack, and I is equal to index, it will column index, it will again get a vertical attack. Similarly for I is equal to 3, it will again get a diagonal attack. That means that third queen, that is x is equal to index queen, can't be placed at any of the positions in the respective column within that same row. Now this is here the algo will do backtrack. It will try to change the position of this queen in the second row, that is index is equal to 1 row. Now index is equal to 1 row, position is being changed. Earlier the position was this one. It will try to go for I is equal to 3, that is the last index. But this again position returns a safe state, yes. Then again that result of first index queen will be equal to 3. Now the next statement says place the queens, that is the third queen, at the respective column. Now if you try to place the queen at the column index is equal to 0, this will lead to vertical attack. So but the next position is try to place the third queen into the index I is equal to 1. This statement will return true. Reason being, there is no attack by any other queens which are existing. The queens being 1 and 2. Now the resultant matrix for the same will be, that means for the third queen, that is second index queen, the column index value is 1. This is 1. Now iterating over the next step, now we have to place now the fourth queen, that is index 3 queen, onto the fourth row now. Now if we try to place fourth queen on the index fourth queen at the uh, fourth row, we can't place this queen here. This will return false. I is equal to 0. This will return false. Similarly, for I is equal to 1, this will return false because there is a vertical attack here. I is equal to 2, there will be a diagonal attack again. For I is equal to 3, there will be again a vertical attack. That means there is no possibility of placing the fourth queen in the fourth row at this position. That means there is no change in the result array. It will remain same. Now what to do in this case? The algorithm will do the backtracking. What will happen in this situation? The algorithm will try to do backtracking by placing this queen in the third row, and by placing this queen by moving this queen forward by one position rightward. Now when it will try to move the third queen by rightward, that means x equal to 2 means third index. Algorithm tries to place the third queen, that is second index queen, into the third row. It is not possible to place the queen here, being a diagonal attack. Similarly, the queen cannot be placed at this position, being there a vertical attack. Now that means no queen can be placed in the third row also. Now what is the algorithm will do? It will further do the backtracking to change the position of this queen. Now as queens are moving forward in the particular row, there is no further position which is possible where this queen can be moved in the forward direction. Now what will happen? This will do backtracking, and it will change the position of the first queen. That means queen first will be changing the position. Now how to change the position? This first queen is being moved forwarded by one step ahead, like this. That means position the first queen in the first index column, it is a safe state because no other queen has been placed so far on the chessboard. Result value will be 1. 1 for the first queen. This one tells the index where the queen has been placed. Now coming to the next situation, we have to place a second queen on the second row. This is not the appropriate position. This is not the position because there is an attack. This is not the appropriate position. The appropriate position will be this one, where I is equal to 3. That means for the second queen, that is x is equal to 1, and I3 is equal to index, and I is equal to 3 column index is a safe state for second queen. The result value for array value for the same will be 1, 3. And moving further, for the third row and the fourth row subsequently, for the third row, you can place the element in the third row and the first column, that is for the third queen and the first column, that is I is equal to 0, that safe function will return true. Result section will say for the third queen, the index column will have value 0. This is the 0 index column value. Now moving further, for the last row, insertion here for the fourth queen is not possible because of vertical attack. Insertion here also is not possible because of diagonal attack. But we can place the fourth queen at this position. This position means the index 0, 1 and 2. This position index is 2. For this placing fourth queen at index 2, the function is safe return yes. That means the final array, resultant array, which represents the final output as 1302. This 1302 represent that the first queen which is to be placed in the first row is stored at index. This solution represents that the first queen in the first row is stored at column index 1, and second queen in the second row is placed at column index 3, and third queen in the third row is placed at column index 0, and fourth queen in the fourth row is placed at column index 2. If you want to explore multiple possible solutions for 4 queen problem, you can continue this step further to explore all the possible cases. That's all for this current session. Is complexity analysis of n-queen problem using backtracking. Now this was the main underlying code of running n-queen problem using backtracking. There was a is safe functionality was there which checked whether the no two queens should attack each other, and this is the main function was the place function which was being used to place a queen at the respective position, every queen on the chessboard. Now the space complexity of for this algorithm is order of n, as the algorithm uses an auxiliary array of length n to store the result in the form of n column positions. This is the result array, which is a linear array. It stores the result in the form of n column positions for n queens. Now considering the time complexity. Now, in case of time complexity, there, if you just go through this code, there is a place queen section, and if you are concentrating on is save function is trying to check whether no two queens attack each other or not. As it is clear from the algorithm that we are placing that every queen row by row, that means there will never be a conflict that two queens are present in the same row. The conflict arises only for the column, that means two queens doesn't share the same column. As we are placing the queens in the different subsequent rows also, there won't be any check for the there is no check for the row section, only column section is being checked. As there are total n columns, that means the loop is here executed order of n times for each invocation of isSave function. Now considering this case, place queens function, there is one for loop which is again executed n times, where size value is n if there are n by n chess row. Within for loop, this isSave function is also being executed. As single invocation of isSave function takes order of n times, as I have previously discussed, if you are running isSave function at the most n times, then the complexity in that case for this case will be order of n square with respect to isSave function. Now this within the place queen function, for every iteration of this for loop, there is again a further recursive call which is one unit less than the previous one. That is, if the complexity of this whole algorithm is t1, tn, the place queen function will be moving one step less than the number of queens. That place queen function will be having the complexity of tn minus 1. As this tn minus 1 complexity function is being executed n times, because this is within the for loop, that means the invocation of this recursive call of placeQueen function within the original function will be n times of tn minus 1. Single is tn minus 1 because it is being called n times, that is n times of tn minus 1. So this is the final recurrence relation for predicting the time complexity of n-queen problem using backtracking. This the same can be solved either by iteration method or recursion tree method. This is the solution for solving the same using iteration method when you expand tn minus 1 in terms of n in minus 1, tn minus 2 plus n minus 1 square and so on. Keep on expanding it, and at the last we are getting this result, and divide both the sides by factorial of n. We are getting this value. By ratio test we can prove that this value is nothing but a constant value. From this we can conclude tn is constant times of n times of factorial. that on the overall the complexity of n queen problem for backtracking is equal to factorial of n. That's all for this session. The topic is solving subset sum problem using backtracking. Now, what is subset sum problem? Let us start with the example. You are given with a set with elements 1, 2, 5, 6, 8. The motive is we have to find a subset if it exists so that the sum of elements of those subset is equal to 9. Now what is the output of this problem? That if you take the elements 1, 2 and 6, its sum will be equal to 9. 1 plus 2 plus 6 is 9. Similarly, if you take the element 1 and 8, its sum will be equal to 9. Now this is subset sum problem. If you want to generalize this definition, given n positive integers, that means the first assumption is all the elements should be positive one, and a positive integer s, which is representing the sum. Find all the subsets of w1, w2 till wn that sum to s. Now one more assumption other than being all elements being is a positive integer, other assumption is there should not be any replication of the element inside the given set. Similarly, one more example, given a set S with these set of elements and we want to find a subset whose sum value is equal to 15. Now the possible subsets from this set are 8 and 7 is where sum is 15, 7, 5, 3 element, its sum is 15, 6 and 9 element, its sum is 15, and 5, 10 element, its sum is also equal to 15. Now generally what we do, from before starting this problem of finding subset from with respect to given sum, we first arrange the elements in the form of increasing order, like what has been shown in this example. Okay, now first start with subset sum problem. If you are applying exhaustive search method on that, let us take an example to solve the same using 4 items W1, W2, W3, W4, and we want to have the subsets whose sum is equal to 15. Now what this diagram shows, this represents a state space tree for exhaustive search where there is a root node. This is basically binary state space tree. This is the root node. From this root node represents the starting point, and this represents that no decision about the given element have been made yet at this point. This is the initial point from where to start. Now, first thing we will choosing the first item with w1 is equal to 3. This level says we will be choosing the first item. Second level denotes that we will be choosing the second item with value 5. Third level denotes that we will be choosing third item with value 6, and fourth level represents that we will be choosing fourth element, that is 7. Now there are two options for a binary state space tree. Either you will be choosing the value 3 or you will be not choosing the value 3. This middle value, these are the middle values. The value inside this node contains the sum of weights included so far. Sum of weights means if you are choosing 3, that is yes is being used, first element you are choosing, so that this will represent the sum of weights which we have included so far. Now that means the left branch represents that you want to include that item, and right branch represents that you don't want to include that item. Now that means 3 here is not included, then sum of weights so far still remains for this node as 0. And when you move further, you will start looking for the second value, that is the value is 5. If you are choosing that value, left represent, you will be choosing that value. If you are now you are choosing that value for the left branch. Now here the that node weight will be equal to 3 plus 5, that will be equal to 8. Similarly, when you will, the second rightmost branch will say that you are not choosing the weight second element item, that is 5. So there won't be any change in the sum of weights. In the second case here, if you are choosing the item or the element with value 5, then weight will be increased by 5. No section right side branch says 5 element will not be chosen, that value will be 0. Similarly, moving for the next level, this level says that item 6 is to be taken into account. If 6 is chosen, the sum of weight so far will be 8 plus 6, 14. If the right branch says 6 is not chosen, it will remain 8. Similarly, for 3 node, 6 will be chosen, the item will be 3 plus 6, that is 9. For right branch says it won't be chosen, then sum of weight will remain same. Similarly, in this case for 5 node value, if 6 is chosen, that value is being taken as 11. Here for the right branch, as element 6 is not being considered, the value of node will remain 5. For this case, if the element 6 has been chosen, the value will be equal to 6. And for this case, element is not being chosen, value will remain as 0. Now moving further, for the last element, that is the last element of the set, that is 7. This represents that element has been chosen. The sum is 21. This represents that element has not been chosen. This left side says element has been chosen, because of that sum is 15, and so on, sum is 8, and so on. In this way you will create whole of the state space tree till the last level. Now the actual solution lies in, because we need the answer with sum equal to 15. This is the actual answer. And what are the how to reach at this leaf node? You will start with that item element with value 3 will be chosen, yes. Then element with 5 value will be chosen, yes. Then element with 6 value will not be chosen, that is w3 won't be chosen, but the element with value 7 will be chosen. That means we will be discarding the third element from the set, and we'll getting the final solution. Now this is exhaustive search, where we consider all the subsets irrespective of that of a given constraint. That means whether we, irrespective of the reason whether that decision is going to be get a fruitful result or not, the exhaustive search considers all the possible subsets. Now, the complexity of this exhaustive search methodology is 2 raised to power n. The reason for 4 elements for exhaustive search, we are getting exactly 16 solution. That is 2 raised to power 4 solution. If there are n elements in the set, the complexity of the algorithm will be 2 raised to power n. There is somewhat better method to solve this sum of subset problem, that is using backtracking. Now, how backtracking is applicable? Let us look into the same problem. Now here, using backtracking, that state space tree, which is a binary space state space tree which is created, is not the full state space tree. It is a pruned one. Pruned one means the last nodes are somewhat not reaching till the leaf level. Some leaf nodes are at some intermediate level. The reason being, the original tree of exhaustive search is further being pruned. That means there is no further exploration of these nodes where cross has been mentioned based upon some constraints. we apply some constraints so that there is no further exploration beyond this node, this node, this node, and this node, and along with this node where cross has been mentioned. Now, what these constraints are? Now, let us take one example. For let us take this case. In this at this level of node value where the sum of the partial weight is 0. Now the new elements which are still required to be considered are W3 and W4, because W2 has been considered till level 2 according to the state space tree. Now that means W3 plus W4 are left. That remaining weights after this node are 6 plus 7, that is equal to 13. If you add that, even if you will explore this node further and the remaining weights are only 13 weights because two uh, elements are left, in that case you won't be able to get the result. The required result is 15, which is less than 15. That means 0 plus 13 is less than 15 here. This directly means that at some moment where your partial weight is there, at some that moment of time, if the remaining weight, if you will add to that weight, the remaining weight, if it is still not serving the purpose of finding the exact value, that is 15, you should not continue with this node. This is a non-promising node. If you mathematically rewrite this sentence, that this sentence says that wixi, that was still this level, that summation of this value I1 to k plus the remaining weights are 13 weights, this should be greater than equal to sum, they should be greater than equal to 15. At least there should be some value which is greater than or equal to 15 for this the consecutive results. Similarly, considering one more case, let us suppose we are at this level, that is 5 is being there. Now the remaining element which has to be added is 7. Now the remaining weights are only one, that is 7. If you will add 7, even then the result is not is less than 15. That means no need to continue further because the result is not greater than sum, it is less than, it is violating this condition also. This is also a non-promising node in the state space tree. Similarly, you can go for this node. Here 3 plus 7, again the value is less than 15. You should stop here itself. Similarly, no doubt this is the last node. Here 8 plus 0, because remaining nodes are 0. Then this inequality also hold true. That means this condition is being violated as written here. Now considering the second constraint, that second constraint is that if the value of till that level, that is till that is this level of the node, that sum of weight values, and if you add immediate next weight to this, immediate next weight after this level is 7, this value should be less than or equal to 15. That means if the value is already exceeding, the next possible option is just to use the next level value, that is 7. 11 plus 7 is already exceeding, that is 18, which is exceeding the required sum value 15. You should not move further with this node. Similarly, this is the case if you will add for this value immediate the next value, that is 7. This value is getting out to be greater than 15. The value here is 16, which is greater than 15. That means we should not move further for this node. Taking the case in the similar manner, this case now 14 plus next element immediate weight to be added is 7. This is exceeding here, that is 21, which is greater than the required sum value, that is 15. So we should not move forward further with this node 14. The mathematical way to represent the same is wixi, and if in the immediate node this already the summation is from I1 till k, and immediate the next node is wk plus 1, that should be less than equal to sum. That means required sum should be this total should be less than equal to the required sum value. If it exceeds that, this is not a non-promising, this becomes a non-promising node. Like this is a non-promising node which is violating this condition. Now taking one more example. Now taking one more example. X1 is equal to 3, x2 is equal to 4, x3 is equal to 5, x4 is equal to 6. There are 4 elements and we want that sum value to be equal to 13. We will have to find those subsets whose sum value is equal to 13. Now we can represent the state space tree like this also, where initial value is the partial weight values. That is, we'll keep on adding the weight values, and this second part is called the total value. Total value is nothing but sum of sum of the values of the elements of the set, total elements, total of all the elements of the set, that is equal to 18. As you will keep on adding a new element into the given, originally the partial set has got value equal to 0 and the total means available value is 18. As you will keep on adding the element to this partial subset, this value, weight value, will be keep on increasing and the remaining or total remaining value will be decreasing by the same factor. Now this example shows x1 is equal to 1 means first element of the set has been chosen on the left side of the tree. Right means first element of, that is x1 of the set, is not being chosen. x1 is 0. x1 is equal to 1 means we are choosing the element with value 3. When 3 is chosen, the resultant weight will be 3, but there will be decrease in the total value by the factor of 3. Similarly, for this case, x2 is equal to 1 for the next level. x2 is 1 means we are choosing the second element whose value is 4. When you are choosing this value, the weight will be increased by 4 factor. That means sum of the weight has been increased by 4, but simultaneously the total value is being decreased by 4. Similarly, going to the next level, if you are choosing x3, for left level branch says you will be choosing that value, right branch says you won't be choosing that value. If now you are choosing this value whose element value is 5, so the weight will become equal to 12 and there will be decrease in the total weight by the same factor, that is 5, 6. In similar manner, you can create the state space tree like this. Now this is a pruned state space tree. The reason, now we will discuss those pruned nodes. What are those pruned nodes? Now let us start with the first node, that is 12,6. Now this 12,6 is basically is violating the constraint number 1. What is that constraint? That means wi summation plus w of k plus 1 should be less than equal to sum. This is the condition for the promising node, but this condition is being violated by this very node. The reason being, the sum till summation of the sum till I1 to k, which is equal to here equal to 12. Now this value is 12 and the element value immediately next to this, that is the value immediately next to this, is for x1, that is equal to 6 for the next element. If you will add 12 plus this next level value, immediate next value, this sum is going to become 18, which is violating this condition. That is, it has already exceeded the required sum value. Now considering the another one more case. Now in this case, we are getting the exact solution. The reason being, the sum, the weight which we have got is already equal to 13, which is the desired weight. Okay, now the case of this node value, the total weight is equal to 0. The weight is equal to 0 and total value is equal to 0. Weight is value is 7. Now it is again, now for this node,
This is not satisfying the second constraint. Second constraint for the promising node is, that means this is the I12k wixi means this value is 7, and the remaining weights sum of both should be greater than or equal to sum is 13. This summation should be greater than or equal to 13, but the sum of the partial sum till this level, that is this value, that is equal to 7, and the remaining weight here, remaining weight is equal to 0 because total remaining weight is 0, that sum is less than the value 13. So this condition is again being violated, that is the second constraint is being violated by this node, so no further exploration of this node will be done. Now considering this node, here in this case, first constraint is being violated. What is the first constraint? This constraint says that sum of all the wixi, that is the partial sum of weights, this is nothing but 8 here, plus the sum of the next immediate element, that immediate element at the next level is x4, that is 6, that sum should be less, that total should be less than sum, that is 8 plus 6 value, that comes out to be 14, but that is not less than 13. So this first condition is being violated here. Now considering the next case, this node is violating the second condition. Now second condition was, thus sum till the weight, sum of the weights till this level, that is 3, and the remaining weight is only remaining is 6 here, because x4 is the only remaining element which is left. The sum of these values should be greater than sum. The total of these values is 3 plus 6, that is 9. It should be greater than this sum value, but it is less than sum value. The second condition is also being violated. Similarly, considering this case is violating the first condition. That means 9 plus, that is the partial weight which we got, 9 plus the value of immediate value of the next sum, that is the remaining value of this x4, that is 6. 9 plus 6 should be less than sum, but it is coming out to be greater than sum. Similarly, this node is violating the condition, that is the second condition. This is violating the second condition. Now basically when you are applying this pruned state space tree, how the execution starts, the algorithm starts with this root node, then it uses DFS for the same, depth first search is being done, then it start exploring this node, then it moves to x2 is equal to 1 this section, then it chooses x3 is equal to 1 this section, then because this is not non-promising and it do the backtracking, then it come forward to the right direction, then it does go to the left direction, and this is the answer. It, after printing the answer, it backtracks its path, and then it tries for the x4 is equal to 0, and this is non-promising, and it again backtraces, and from this it again backtraces, from this again it backtraces, from this again this move forward to the right direction. In this right direction it goes to the left. This is nothing but DFS search, and this is non-promising, and it again go back to the previous node, and again try to go to the right of this node. This is non-promising, and again backtrack from this node, again backtrack from this node, again backtrack, and after coming to this node, it try to explore the right of this node. It comes here, and then it explores this one node, then it comes here. From here, this is non-promising, and it backtracks. It try to explore the right portion of this tree. It is a non-promising node, it backtracks, then does a backtrack, it tries the right end of this branch, it backtracks from here because it's non-promising end. After backtracking this, it comes to this section, it again backtracks till it reaches the starting vertex. This is nothing but depth first search for this state space tree using the backtracking mechanism. Okay, these are the promising condition which we have already discussed. That is the partial weight sum Wi xi can be either 1 or 0. That means that particular element, whether it has been chosen or not, depending upon that we will get in this simulation. If the partial sum is still k elements, and then immediate next element, that is wk1 plus 1, if the sum of both should be less than the desired sum value. Similarly, the second promising condition is the partial weight values, that's the sum of partial weights values plus the remaining, all the remaining weights, that is all sum of all the remaining elements which you have not considered so far, that value should be greater than sum. These are the two promising conditions. If either of these promising condition is being failed by any given level node, that node will not be explored further. That's all for the current session.